So let's see, integration theorems. So what is the main inspiration for integration theorems? The main inspiration is, again, the theory of integration in a single variable. Exactly the same way that in the previous section, we said, let's try and generalize the theory of integration over intervals in the real line for single variable functions. This was the motivation somehow, that we wanted whatever that theory looks like in 3 dimensions. And so we had to do a lot of work to make sense of what intervals now become. So intervals on the real line are the most general kind of sub region of the real line, right? I mean, you can have collections of intervals if you like, but essentially it's either the whole line, half of the whole line, infinite line, or intervals, right? There's nothing else in terms of shapes. Now in 3D, there are many, many more shapes. In particular, shapes with definite dimension. We have points, we have curves, we have surfaces, and we have volumes. So we had to do all this work to develop the theory on how to describe those objects, right? 0 dimensions, points, not need to describe anything, just to specify the coordinates of the point. 1 dimension curves, we need to specify parametrization. You have all the whole business of tangents, cotangents, normals, and all these things. Then you have the business of surfaces, where you define again a parametrization, you take the normal, you choose orientations, etc. And then we have the business of volumes, in which you're describing essentially as regions of your coordinates, but then you're also thinking of volumes as something that can be parametrized somehow, or sometimes you'd like to think of that as changing coordinates, perhaps. Again, with the whole business of you have a Jacobian, or you have parametrization vectors that give you a different basis at every point of your object, and so you can compute the unit volume and so on. This is sort of going back to all the previous material that we've talked about. Now, all that effort was done so that we can have a full theory of integration, as we said. Now, what is the basic result of ordinary calculus? This is, of course, the fundamental theorem of calculus, as the name indicates. And the fundamental theorem of calculus that I'm going to write like this tells us that if we are integrating a function over an interval AB, so actually, let me just get rid of this notation. So let's say I. Now I is an interval AB on the real line. So if we integrate of some function, some differentiable function, over the interval I, this is I, which goes from A to B, this is the same as doing f of B minus f of A. Right? This is the fundamental theorem of calculus. So I want you to look at this result from a slightly different angle from where you're used to. So this result is telling us that some function that happens to be the derivative of some other function, but some function, which is our integrand, when integrated over an interval, actually becomes just the value of some other function at the endpoints of the interval, right? So forget about whether it's the derivative or the antiderivative or whatever, but what this is telling us is that a one-dimensional integral, doing an integral over a full interval becomes, quote unquote, 0-dimensional integral. That is just evaluating at points at B and A, right? And there is some sense of orientation, because there is a sense that the interval is traversed from A to B, so that evaluation on B is left with a positive sign, and evaluation at A is left with a negative sign, right? So that is to manifest the fact that we are traveling from A to B within the interval I. So the I interval has an orientation. So actually, the basic concept of integration theorems is already present in the fundamental theorem of calculus in a single variable. But it's a little bit redundant to make a fuss about how this is, a one-dimensional integral that turns into a quote-unquote zero-dimensional integral. So don't worry too much about the term zero-dimensional integral. That really just means evaluate your function, right? It's just to be consistent with saying n-dimensional integral, because that's going to be the point today, for n being 0, 1, 2, or 3. So what happens in 3D? What happens in R3? So in R3, if we see an integration theorem as a result that relates an integral over over two different objects of dimension, right? So of two objects of different, then and relates the integrands and the functions with some differential operator, in this case just taking the derivative, then in R3 we should be expecting three integration theorems. So why should we expect three? It's because we have three jumps in dimension, right? We have from 0 dimension to 1 dimension, we have from 1 dimension to 2 dimension, and we have from 2 dimension to 3 dimensions, right? So let me actually list them that way. So from dimension 1, sorry, from dimension 0 to dimension 1. How do I want to write them? No, the opposite way. So dimension 1 to dimension 0, dimension 2 to dimension 1, and dimension 3 to dimension 2. Right? Okay. Let me take this thing. Let me take it down a little bit. Okay, whatever. Dimension 2 down here. Okay, so we're expecting 3 because we are in dimension 3. So we have objects of all these dimensionalities. So there are 3 jumps in dimension, right? So what is the integration theorem for dimension 1 to 0? Of course, this is what we call in this context the fundamental theorem of calculus as well, because it's going to look exactly in the same way. And because the reason why we call it the same name is because it's the same jump in dimension. That is the connection to the usual fundamental theorem of calculus. Sometimes it's also called fundamental theorem of calculus for conservative fields and things like that. So how do we write it? What is a field in this case? So the field is going to be a function. And so if we have a curve, so actually, how did I want to write this? Yeah, so let's have the code that your geometric object is in blue and its boundary is in red, right? So let's call this P and Q. Actually, the other way around. P and Q. And let's call the curve C, right? So the integral of now differential operators, so some function f. So I'm going to specify what object we're talking about in each case. So this is a function from R3 to R. This integral will be the integral over P and Q. So this will become an evaluation at P minus an evaluation at Q. So let me just use the color code because I think it's nice. Actually, let's make it very pretty and use our arguments, function arguments also in color. So you can see the parallels, you can see the structure of integration theorems. So of course, so this is F, F, F. And of course, we do a line integral C and we do evaluation at particular points, so P and Q. Sorry, I forgot dr. Right, so from a function, we compute a vector field, which is the gradient. And so we have one notion of vector integral for a line, for a curve. So this is the line integral. So we take the line integral and that becomes the evaluation, right? Okay, so that's the one-dimensional integration theorem. What about the two-dimensional? Okay, so let's have a look. Let's draw the boundary first. So let's do something like this. And right, so I hope it's clear that it has some volume S. It has some surface. And perhaps I can shade it a little bit. Right, so we call C the boundary. And so what we're integrating now, so we have we have two surfaces. So I have a surface and a line. So what I need is a vector, because we can integrate vectors over both things. So our field, or our integrand, will be a vector field. And so again, same pattern. Surface integral. Okay, perhaps yeah, perhaps let me use double integral sign notation in the theorems, so you see them more clearly. I'm going to be integrating a differential operator of my field, and then this would be a vector field in itself, and so that I would do surface integral, so dot ds vector, and this will become now a one-dimensional integral, so single integral over a curve, and that will just be the ordinary. Oops, should not be the R, right? So now I fill in with the colors so that you see where things manifest. So our integrand appears in the higher dimensional integral, it appears under a differential operator, and in the lower dimensional integral appears as it is. And then the surface integral, well, it's just blue, and the curve, the line integral, is C, which is the boundary of the surface. That's the relation. That's why I keep consistent the two color codes, right? Okay, very well. And then lastly, this is a bit harder to draw. The reason why it's a little bit harder to draw the three-dimensional case is that the way we have intuition of three-dimensional objects is actually by seeing their boundary, right? If you think about it, unless you're thinking about something that's kind of fractal or kind of diffused, like a cloud or like smoke or something like that, the way we understand three-dimensional objects is actually by having a precise sort of intuition of their boundary. So it's kind of hard to draw the inside and the outside at the same time, but I'll do my best. So I have to draw a red surface, closed surface. This is the thing. So this is a closed surface, S, and then there's bulk inside. It's sort of like blue bulk inside. So maybe with dots it's a bit clearer. This maybe makes a little bit more sense to put dots inside. And so that's what we're going to call B, right? So it's inside, it's the bulk. So let's make the dots a bit more dense around B. So I think I hope it's clear, right? So S is the boundary, B is the bulk. Okay, so then and again, if I'm going to do an integral over a surface and I'm going to do an integral over a volume with some differential operator, I need a vector field again. And this is so that we can make sense of the formulas. So now, same idea, three-dimensional integral. We're going to integrate now some function. There's only one way to do three-dimensional integrals here. This is going to become a two-dimensional integral. And now with the ordinary vector field. So this will be a surface integral, so dot S. So again, exactly the same pattern. You can see the one above, and I will just copy the color code, right? So my integrand first appears under a differential operator. So in this case is the divergence, because indeed I need a function to integrate over the whole volume. And then the other side of the integral is just the vector itself, the vector field itself. So it's just the integrand on its own, just like before. And then color code for the boundary, for the bulk, sorry, and then for the boundary. And there you have it. So it's exactly the same pattern, right? Okay, so this is it. This is the three integration theorems of R3, hopefully summarized in such a way that you can see they're really all the same part of the same story, right? Like they are manifestations of the same fact, the same sort of fundamental phenomenon in calculus, right? In this with these constructions. So okay, so if you want, I can. We're around the time, but it's also true that Lucy came a bit later. So I'm happy to give you some comments, some insights, some interesting facts and things to know from these theorems from this point. But please, questions. I mean, this was just a summary. Of course, I didn't flesh out what these theorems are saying. I just said this is how they look like, and hopefully you see the symmetry. So comments, questions, please. Yeah.
Sorry, I was just.
Okay. So, yeah, Alicia, go first. Yeah.
Why are both the big F's, capital F's, R3 to R3?
So again, the actual mathematical reason for this is a little bit deeper, but at this point you need to consider the following: the derivative. So we in the context of calculus. So this might be worth listing somewhere. So okay, let's maybe all looks like a so let's briefly speak in the language of differential operators. This is a very relevant question. So so the notion of differential operator. So what is the differential operator in R? So differential operator right? So in a single variable function context, the differential operator is the derivative. There's nothing else, right? I mean, you can define other differential operators, but the basic one that just from which you can build all the other differential operators is the ordinary derivative. Now, in our context, so in our context, we have the following. So we have functions. So let me use this notation. It's a bit of more grown-up notation, but it's very useful. So let me use this letter. Actually, I don't even need to specify it's R3. We're only working with R3. So I'm going to use this curly F to designate all the sufficiently differentiable functions of R3, right? So this is a fancy letter to designate the family of all possible functions, right? It's the set with all the functions inside, abstractly, sufficiently differentiable for our purposes, okay? And let me use curly V, a fancy notation for the same thing. All possible vector fields that are sufficiently differentiable, that have components sufficiently smooth for whatever purposes that we want to write formulas about. Okay, so we have those two sets, and these are so the same way that R3 is the stage. We're thinking of it as sort of the the setting where things are going to happen. The stage of an opera. The functions, the F and V's, are the actors, the singers, and the musicians bringing things to life, right? So so that's how you should be thinking about curly F and curly V. That these are sort of the characters that are going to populate our world, R3. Okay, but now, what are the natural? Where are the natural? So of course, our world is going to have interesting features and landscapes, and that's curved surfaces and volumes, and our characters will inhabit those interesting places. And then integration theorems is sort of like what happens when characters interact with their environment and so on. But characters themselves have relationships, right? Like they become friends. One turns into another. Someone is someone's enemy, and then changes, and they go through plot lines. So, what is the idea of plot lines in this context? Well, this is the idea of differential operators, right? The same way that you could be thinking of your characters in ordinary calculus, single variable calculus, as single variable functions. These are the things that populate the real line, right? Differential operators in this, which are all generated by this basic differential operator of d by dx, the derivative. These are sort of the character development devices, right? So these are the things that turn one character into another and things like that. So in that same sense, we have more than one now, and we have more than one kind of character, right? We have now functions and vector fields. These are the two kinds of characters of our theory in R3. And so the idea is that differential operators now so actually, let me just do it on the side because I think it's going to be nicer if I can. So let me just talk about differential operators here. So there are several differential operators, right? If you think about it in detail and you go back to the definitions, you would notice that these differential operators are somehow natural, right? You're not throwing some random combination of partial derivatives. These objects actually define vector fields that transform well under changes of coordinates. So this is a little bit more sophisticated than what we are intending in this course. But the reason why there's only 3 differential operators boils down to the fact that if you just put together a random combination of partial derivatives, if you change your coordinates, you're going to get something that looks very different, right? So this is essentially the reason why we are only sort of limiting ourselves to 3 differential operators. So which are the 3 differential operators? So the differential operators are the gradient. So what is the gradient? So let me actually put the name, because otherwise the symbol is going to look very similar. So the gradient is a map from functions to vector fields, right? Given a function, you compute its partial derivatives and you plug it into the components of the Cartesian basis. Okay. What is the curl? This is an operator that sends vector fields to vector fields, right? You compute with the formula, whichever way you like, and then it gives you this idea of the torsion of the vector field, somehow the infinitesimal torsion of the vector field, the same way that the gradient gives you the direction of maximum rate of change. The curl somehow encodes this idea of torsion, right? Of how much the vector field is curling, hence the name. And then finally, the divergence, which is nabla dot. So nabla dot, of course, takes a vector field and gives us a function. So what is this function? Well, the function is of a vector field is encapsulating essentially how much the vector field is expanding. If you think of it as the field of velocities of some fluid, it would give you an infinitesimal sense of how much the vector is expanding or contracting, right? Again, so you can think of these 3 differential operators from a very simple point of view of from the point of view of vector geometry, right? So if you abstract for a second and you think of gradient, curl, and div as, sorry, of the del, right? So so some people like to think of del as a vector. So that symbol, that flipped delta, we call the nabla, right? That symbol with a vector, that people like to think of it as a vector, you know, partial in the first component, partial x, partial y, partial z as a vector. There's some problems with that interpretation, and it gets a little bit beyond what we want. But essentially, if you have a vector, and you have scalars and vectors, right? Scalar fields, functions, vector fields, vectors, right? There are 3 ways in which you can combine these things, right? You can multiply a scalar by a vector, and it gives you a new vector. You can multiply a vector by a vector with a cross product, and you can multiply a vector by a vector and get a scalar with a dot product. So the way to remember that these are the fundamental operations in 3-dimensional geometry is to remember that these are the fundamental vector operations, right? That grad, curl, and div are the basic operations of the field-like objects, in the same sense that scalar multiplication, cross product, and dot product are the fundamental operations for the vector objects, right? That sort of point-wise linear objects. Okay. So, okay, is everyone with me so far with this notion of differential operators?
Yeah. Yes.
Okay.
Okay.
All right. So your question. So this was the preamble to the question. Your question is why do we have in dimension 1 to 0 we have R3 to R, and then in dimension 2 to 1 and 3 to 2 we have R3 to R3. So the reason is because of the pattern of the differential operators, right? Look at the pattern. First level F to V, second level V to V, third level V to F. So the integration theorems are reversing the direction of the differential operators. I mean, you should really be thinking. I mean, there's a reason why people call the theorems. They call them the gradient theorem, the curl theorem, and the dip theorem, right? Because that's essentially the content of the theorems, right? In the first one, you say, well, what can you say about the gradient operation? Well, you can say that if you integrate the result over a curve, it will be the same as evaluating on the extremes. Again, what can you say about the curl operation, which is for a vector field? And then you say, well, that if you integrate the surface integral of the whole thing, it's the same as the result on the boundary. And then again, what can you say about the div operation? The divergence is again the same thing, that integrating in the bulk, the result of the divergence is the same as integrating the argument on the boundary, right? So integration theorems can be seen as this sort of integral dual of the infinitesimal differential operators, gradient, curl, and divergence, right? So the reason why you have F vector scalar field for the first one and vector field for the other two is because that's how your differential operators work, right? So you might be thinking that that's somehow asymmetrical, but actually, I mean, the reason why it looks asymmetrical is because we are really just looking at R3 and we are forgetting about the dual space. There's something called the dual space, but this is for when you learn a little bit more linear algebra. But actually, that asymmetry is not so much as you think, because if you look at the first problem, first theorem, you would see that the theorem on the equality on the right hand side is evaluation of a function, right? So it involves something with a function, right? The equality on the left hand side is an operation on a vector field, right? So the equality is exactly in the same order as the gradient, taking functions to vectors. So this is something that relates a vector to a function, right? And that's why I wrote it in that direction, so that we reverse the direction of the differential operators. So we have right hand side function being evaluated, left hand side or integrated, and left hand side vector field being integrated. Now, in the second theorem, we have vector field being integrated equals vector field being integrated. And then in the third theorem, we have function being integrated equals vector field being integrated. So actually, there is full symmetry in terms of what we are integrating. It just so happens that the way we move between one or another is written that way. And so basically, the reason why it looks asymmetric is because I chose to give it a name to the field that we act with an operator with, right? And not the result of that action, right? If I had taken that, then you would see that the last theorem will be talking about some scalar field, some function, such that there exists some vector field of which it is a divergence. In which case, the argument here will be some little g or something, which is a function such that there exists an f that div f is g, right? So g will be again a function from R3 to R, right? Does that answer your question?
Yeah, I think so.
Mm-hmm. So again, it's a pertinent question because it highlights what the integration theorem, or it's a way to get into one of the ways that integration theorems work, which is you don't need to start by having an integral that looks like surface integral of the curl in the case of 2 dimensions, right? You could have surface integral of a vector field, and then you can wonder, you can ask yourself, can I find a vector field such that if I compute its curl, I obtain my original integral, right? So the situation is as follows. So if I have an integral that looks like this, some vector field G vector yes, you might wonder, does there exist an F vector field such that G equals curl of F? Because if it does, then your integral, by virtue of Stokes' theorem, of the second theorem of integration, becomes the integral over the boundary, which might be simpler, right? So this is a very relevant way of approaching these integration theorems. This is a very relevant intuition to have about them, that even though they look very explicit with the differential operators in one of the integrals, you can actually make them appear that way in general situations, right? And so this is the whole business of finding inverses for differential operators, right? So if I give you a vector field, can you find me a function which is the gradient? So this is something. Yeah. Is there a question?
Yeah. Can you find the gradient function of a vector field? So could you without the dot product or the cross product? Is there anything defined as that?
Yes. So in principle, you can do that, in the sense that nothing's stopping you from taking partial derivatives of the components, right? So,
so you couldn't then integrate it, because then you'd be wait.
So
yeah.
okay, so your question is pointing towards something that is very important, and that we actually talked about it tangentially in this course, but
you could find the first one in the same way if you could take the gradient of a vector field where it was f of R3 to R3, because then you couldn't define it the same way. You couldn't have the output being then vector output of
no,
f.
so but let's just think. Okay, so before we think away from this, just think about how you would compute the gradient of a vector field. What would you do in practice to do that?
Would you just find the it's a good question.
So you have, with a vector field, you have three components, right? Each of them is a function. So what could you do in principle? Very simply.
Just differentiate each of those functions with respect to each of the variables.
Right. So each of the components is a function. So the gradient for each function gives you a vector, right?
Yeah.
So suddenly you end up with three vectors instead of one. No, but so this is I mean, you're pointing towards something very important, which is a lot more fundamental than all this story. All this story is somehow special to R3. It's because we have dot products and cross products. R3 is a special realm in terms of the geometry, and we are definitely exploiting the geometry constantly, right? Like we're thinking of curl and div, all these operations explicitly and strongly use the geometry of the space. So, however, if you think very generally, the question that you're asking is, in the same sense that the generalization of derivative for function was the gradient, because we did say this at one point. We did say that there were many different directional derivatives, but if there was one notion of derivative for a function, it was not one partial or another partial, but it was the vector of partials, right? Because it allowed us to compute all directional derivatives as linear combinations, right? You remember this?
Yeah.
Okay, so in that sense, it's a very natural question to ask, which is your question, but slightly reformulated, to ask, is there a similar operation for vector fields, right? Do you have a map from R3 to R3, which is you're interpreting as some form of vector field, but is there a natural notion of a single object that is the derivative of the field? Because curl and div, they don't look like the derivative of the field, right? They look like we are asking something quite special. We're saying the curl is somehow telling us how the thing is sort of twisting, and the divergence is not even a vector field. It's some scalar that is telling you how much it's expanding. So it looks like we're losing information in both questions, right? One is about the twisting and the other is about the expansion. But it seems that there's more to how the vector field is changing than just expansion and twisting, right? You agree with that?
Yeah, definitely.
Okay, so then the point is that the general question moves to what is the differential or the derivative of a vector field, and this is what we call the differential map in mathematics, or the tangent map, or in the context of very explicit components and partials, this is what we call the Jacobian matrix. So indeed, you have a map that I mean, this you've seen. The Jacobian is something that you've seen, right? Because it is something that you had to compute for the determinant Jacobian, right? For the change of coordinates. So this is actually what you do with vector fields. So vector fields, the grad of a vector field, so to speak, will be what we call the differential of the vector field, and that would be made of all the possible partials of all the possible components. 3 by 3, 9 entries. It's a matrix. It's a 3 by 3 matrix, and that's called the Jacobian matrix, or the differential matrix of your vector field. So it's a very pertinent question, but it's not. But this takes us outside the realm of integration theorems, because what's important in integration theorems is that you stick with this idea of a differential operator that maps between these objects. So the Jacobian matrix is a differential operator in some sense, but it takes us outside of the actors of our play. The actors of our play are functions and vector fields, right? We don't have a thing that is a matrix field. These things are sensible, and they are indeed considered in more advanced theories, and these in physics are called tensor fields in general. But at this stage, this is what we are dealing with. So if you restrict yourself to functions and vector fields, this is all you can do, right? And this is all the constructions. But very good question.
Can you hear me?
Yeah, I can hear you.
Okay. I really want to find out more about tensor fields and stuff like that. I find it so interesting. But yeah, cool. Thank you for that. For that answer. That was really interesting.
Okay. So that's basically what I wanted to say about the integration theorem. So a few comments that are relevant for your more practical approach to these. That's thinking of how the tensor field. So sorry, how the tensor fields, how the integration theorems apply. So notice something, right? In all these situations, if your boundary happens, so if your geometric object, right, higher dimensional geometric object, your blue object. This is why I'm not making use of my own convention. I use colors to refer to them more clearly. So the blue objects in the theorems, right, they are general objects, right? Any curve, any surface, any bulk, right, of volume. So, and then the red object is given by its boundary, right? Its geometric boundary. Now, what happens if these objects don't have boundaries, right? That's a reasonable question to ask for the blue objects. The red objects never have boundaries because they are the boundary of something. I mean, if you do a little bit of mental imagining, you would realize that things that are the boundary of something can never have a boundary. This is a funny fact that you probably never reflected upon, but it's true. But the blue objects are completely general. So what happens if they are in fact closed? We call in mathematics closed, meaning no boundary. Well, let's go case by case. So in the first case, the integration theorem could be reformulated by saying that C has no boundary is the same thing as saying that P and Q are the same point, right? That if you were to find a boundary point, it would actually be the same at both ends. So the integration theorem would read integral over C equals evaluate at P minus evaluate at Q, but P and Q are the same point. So obviously that's F of something minus F of something. So it's 0. It's two values subtracted. So in that case, so we say when C is closed, so you know, what you can interpret as P being Q, we have this following notation. So when C is closed, we indicate it, let me write it more clearly. We indicate it by a little circle. Come on, can I draw? On the integral, just like that, right? So of course, the integral is 0 in that case, right? And so this same idea for the surface S, when S is closed. So S being closed means that your curve is actually a single point, if you want, right? So, or you know, or empty, if you like. I mean, you can see it in both ways, but I think it's clearly to see that your curve C actually becomes a point, a set of a single point. So obviously, a surface in a line integral of a single point is 0, because, you know, would be, roughly speaking, the length of the interval times, or the length of the curve times whatever function, but the length is already 0. So this is where you get a special situation. So clearly the left-hand side integral will vanish when there is no boundary. So again, we use this notation of a circle as, and in this case, this vanishes. Here. Okay, and well, to talk about B having no boundary will mean to be talking about doing an integral over the entirety of R3, right? So if your field is well defined and is integrable and differentiable for the purposes of this, integrating over all R3 will always give 0 for divergence, because I mean, divergence is, roughly speaking, asking how much are you expanding outside of some region, but the region is everywhere. So the answer is nothing, because you can flow outside of your own reality, so to speak. Okay, so actually, that being said, so this is another interpretation of the theorems, right? I mean, let me just say here, when B, I mean, B closed, that doesn't make sense in R3. So B, but B can be R3, which has no boundary because it's the entire space. In which case, I mean, we don't use the circle notation for the integral, but we do use R3 as an integration domain. We have this. So this is another interpretation of the theorems. So the theorems have these sub-theorems, or corollaries within them, which speak about the regions being actually, yeah. Let me use the color code because it's nice. S and B, and yeah, let me use the color code for boundaries, P and Q, and here you have C, and nothing there because there's nothing else to say. But yeah, it's another interpretation of the integration theorems. Now, one last comment I want to make. Well, two brief last comments. One is, once you fix a boundary, right? And so instead of now thinking there's no boundary, let's think there is a boundary and it's fixed. This is the first thing we consider. Then if you just look at the right-hand side of the theorems, you see that these are theorems about evaluating functions, computing line integrals, or computing surface integrals of arbitrary arguments, right? F can be anything. F vector, F scalar can be anything. So you can also read the integration theorems from right to left and then say, if I want to compute this thing, you know, left-hand side, this thing, I can go to the right-hand side. So, sorry, I want to compute right-hand side. And so right-hand side is completely general. C can be anything. I mean, sorry, not general, has to be a closed curve. So C is fixed, so it's a boundary, so it's a closed curve, and I want to compute it. I want to compute for this closed curve an arbitrary f. I want to compute the line integral. That might be hard, and it's possible that you could simplify the problem by going to the left-hand side of the theorem and computing the curl of f, which is always direct, and then finding a surface whose boundary is C, right? So this is the other way that, and in fact, the most powerful way to apply integration theorems, which is to transform possibly hard low-dimensional integrals into possibly easier higher dimensional integrals, right? So the first case is a little bit redundant, because obviously if you want to know the difference in value between 2 points, I mean, the easiest thing is to evaluate always. But it might be theoretically relevant for some proof or in some context to actually express the difference of a function as the line integral of some gradient, right? And because you might want to express things in terms of integrals for some reason. But the other two theorems, Stokes' and divergence of Gauss's theorem, gives you that general idea of giving a closed object, closed curve, or closed surface, you can find some arbitrary surface that fits as a boundary, and then compute the curl or the div, and then possibly make your integration easier, right? Now, you might be asking, in what sense can I choose different B's to be the bulk inside S? And this is the thing. Our intuition is not good at seeing that, because we have intuition of objects as shells, right? As regions with a boundary. But how you should be thinking, because obviously it's very intuitive that if I fix my red curve in the second theorem, right? I fix C as a boundary. It's very clear that you can imagine S as being this soap film, that the soap bubble that is constrained to live on C, but it can be any shape, and all will work, because the theorem says that as long as C is the boundary of S, and as long as you're integrating these precise fields, F on the right-hand side and its curl on the left-hand side, the theorem holds, right? So the business is that you can search for any surface that fits your problem. The vector field might have some symmetry that can be reflected by making the surface look that way. It might have some spherical symmetry, so you might want to use something that looks like a spherical cap or things like that, right? So the reason why in the third theorem is not so easy to see is because what the idea is that B could be sort of stretched and twisted inside of the region S, as long as inside of the shell S, as long as it's actually enclosed by S, right? So intuitively speaking, it's like your space will contract and bend and so on within S, but S will be rigid and fixed, okay? But so how that translates mathematically is that you can choose different parameterizations and coordinate systems of your bulk inside of B, okay? Okay, so unless there's a question about that, my last comment is about the interpretation of these three theorems, which is, I mean, we've already discussed. Actually, we've already commented on, and the basic idea is already given. So remember how in the three integrals and that we define, in the two vector integrals that we defined up here, we had a very clear intuition of one representing to what degree f is flowing along the curve, right? In the first instance, so this is what we could call the circulation of f along the curve, and in the second case, this was a sense of how much f was going through the surface. So this could be understood or interpreted as the flux of f through the surface S, right? So circulation is line integral, just seeing how much we are flowing with the direction of the curve, and flux is how much we're going through the surface, right? And so if we have these two concepts in mind, then these integration theorems are super nice, and they give you, actually they could be the way that you interpret your differential operators, in fact. So let's see. So the gradient, we already have a good intuition for. The gradient is saying something about how the function changes, right? It's telling us the direction of maximum change. So this idea is that how to read the first theorem is to say the total change of my field between P and Q is the same as doing the incremental changes of how my function is infinitesimally changing alongside any path that connects P and Q, right? This is the intuition. It could be any path. You could go backwards, far away, and then come back. The idea is that by doing an integration of the gradient, you're sort of keeping track of an accumulation of data, right? But it evens out in the end if the function is well behaved. So because remember that if you're going far away and your function is somehow decreasing, then and your gradient, your function is decreasing, so your gradient is not in the direction of your curve, then that would be a negative contribution. And then if you go in the direction of the function increasing, your gradient will be in the direction of the curve, so the dot product will be positive, so that will be a positive contribution. So the theorem says that those effects exactly even out, right? And at the end, you have exactly, regardless of the path, you have exactly the value of the total change as the integral of the gradient along the curve. So what about the second one? Well, we did mention that the curl is related to the rotation or the twisting of the vector field. We didn't really justify it. You can see some animations on YouTube. You can see the Wikipedia article, as well as some of comments in the textbook. The textbook also has some comments on this to get some intuition of why the rotation, the curl is talking about rotation or twisting. But in any case, you can actually see that being expressed in the theorem, because it says that the circulation of F around a closed loop, the red C in this diagram, equals some surface integral of a vector field, right? So this vector field is somehow, so you have a flux of a vector field through the surface. So what this vector field should be doing is telling you how much your vector field is rotating, so that when it goes through in terms of sort of a right-hand side, a right-hand rule kind of situation. So the basic idea, the animations you'll probably see online have to do with a disk that is rotating. So you see a little disk with circle as a boundary, and then you will see how when you compute, you take some vector field that flows along the boundary of the disk. Its curl is precisely vertical, and so it represents rotation. So that's basically what the second theorem is telling us. So it's perhaps a little bit less intuitive, because there's this notion of the flux of something that is not so clear, which is the curl. But the third theorem is super intuitive, because again, divergence is, again, you can see some animations and see some proof in the textbook or elsewhere where you get a justification of why divergence actually encodes this idea of how much of a vector field is expanding or contracting. Even if you don't know this, the theorem is kind of telling you what divergence means, because the theorem says if you fix a surface S and you give me that is closed, right? So it encloses some bulk, some volume, and then you fix them and you give me some vector field. That vector field will be, coming in and out of the surface in complicated ways, in principle. So the idea is that the double integral S over F is the flux of F through a closed surface. So it should encode how much F is in total coming out of the surface, right, or coming in. So if it's positive, it will be a net outwards flux. If it's negative, it will be a net inwards flux. And the intuition is precisely that you can compute this number, the net flux of a vector field, by computing how much the vector field is infinitesimally expanding at all points in the bulk. So this makes sense. At least to me, it sounds very reasonable that a bulk can be infinitesimally expanding at all points. So you integrate that notion all over the volume. That should be the same as how much the vector field is flowing inwards or outwards the boundary. So that's how you interpret this theorem. So by the way, just notice that you could write the integral here in Stokes' theorem with a circle, and the integral in the Gauss's theorem or divergence theorem with a circle, just to emphasize notation. But we can leave it at that.